Hello, thanks for joining us today. We're talking about 6-1. Now we will move our attention to rate graphs. The rate graph question is almost always an FRQ question for both the AB and the BC tests. It is one of the most important questions you'll learn how to do. We will revisit this topic time and time again. It can be pretty complicated. In this video, I'll try to give you some guidelines for your answers, and in a following video we'll work on a problem together. So graphs of rates are very common in calculus. Frequently we will know the rate of a quantity, and we would want to find something related to that rate. This is similar to the related rates lesson where we had two quantities that were both changing, and we knew how one was changing, and we could find how the other was changing. This is more like knowing how one rate is changing and talking about how the quantity that rate is associated with would change in response. So the horizontal axis, it often stands for time. Often stands for time. Not always stands for time, but often will. The vertical axis, on the other hand, will stand for some type of rate. Okay? It's not always going to use rate. Sometimes a lot of these tricks could be used for anything, any kind of graph, but it'll often be about time. And our y-axis, when we're talking about a rate graph, is a rate. So this is kind of the bare bones version. The point on a graph would be a value at a certain time. Okay? Would be a rate at a certain time. It would usually be measured in units per units. This is a little confusing. We're going to break it down in a second. The slope or derivative of a rate graph would be the rate of change of a rate, and that can be very confusing. The signed area, also known as a definite integral, use all the colors, the signed area between the graph and the horizontal axis will be a definite integral, which is an accumulated value. So in this context, and in many contexts throughout chapter 6, we're going to be thinking of the integral as an accumulator. Now, don't get too worried about this. You've already been doing this if you follow the lessons sequentially. For instance, a normal type of rate, velocity, would be a rate of distance, or probably more specifically, let's say position. So the rate of position is changing over time, feet per second. And you've already done this in many examples where we would give you a velocity graph and ask you what a point on that graph represents. Well, it would represent that the velocity at such and such time is 50 feet per second. Now, the derivative of velocity, the slope of velocity, is the rate of that rate. It just happens that for velocity graphs, we have another word for this. We call it the acceleration. And it's measured in feet per second. And sometimes we will shorten that to feet per second squared. But that's what we mean by feet per second. See? And lastly, the definite integral of velocity, this is something we just recently covered in chapter 5, would be the, and I don't ever want to hear anyone say this on a test, and I'm sure the AP people feel the same way, accumulated velocity. And this is why this part will be the hardest to interpret. The accumulated velocity, that's nonsense. That's a nonsensical answer. Please do not write that. So what we really mean by the accumulated velocity, if you've been memorizing everything throughout the homeworks, that would be a displacement integral. I guess I should have bounced, sorry. A displacement. A change in position. And this unit would just be feet. So that's a useful example to keep in mind. We'll do another rate example, like I said in the next video. But right now I'm going to give you some tips for every rate problem you'll ever do. And in a lot of cases for any kind of graphical interpretation you would ever do. Here we go. So, this is a sentence frame. You would be able to use this sentence frame when you're asked to interpret a meaning of a point. You're basically always going to write at the x value, remember to include units, the y meaning was whatever the y value is. So for my velocity graph, at 5 seconds, t equals 5 seconds. This is just a sample. The velocity was 75 feet per second. Okay? There's a sample sentence. That would be for a graph like this. That can be a little more specific. We'd have that is 75. And that was 5 seconds. Really wacky scale, but that's the idea. Interpret that point. Oh, at 5 seconds, the velocity was 75 feet per second. Okay? Now it gets a little harder. Explain the meaning of the slope or the derivative. So one thing you want to focus on is the units here. The units are always going to work out to be a y unit over the x unit. This comes from the slope or the derivative equals a change in y over a change in x. So it's not more stuff to memorize, but if you know the slope formula, the y units over the x units, that's what we're talking about here. So between the x range, the y meaning was increasing or decreasing at a rate of, and this should always be absolute value of the slope, the value of the slope, or the absolute value of the derivative. You should note that if it's a derivative, we're not going to be talking about an x range. We'll be saying at. So at such and such time specifically, because for the derivative it would be an instantaneous rate, whereas for the slope it's an average rate. So careful about this. This could also be an at x value. Okay? For the derivative. Okay, next. Explain the meaning of an area or integral. This one's the hardest one for sure. Very careful about these questions, because explaining the meaning is usually the hardest. The units will be a very good guide here. That would be an x unit times a y unit. And that's because the integral comes into play here. We have f of x, my y units, times my dx, my x units. Measuring that in the y unit, whatever the y unit would be, and that in the x unit. So, between, and here we'll always have some sort of x range, the net gain or loss of, and this is very hard, but that's where we'll say the accumulated value. So this could be a total, or an accumulated amount, or something else. And I know that's not helpful, but what I want to urge you to do is to check units. Frequently, you'll have a nice explanation based on the units. And then here should always be the absolute value of the area's actual value, or the absolute value of whatever your integral was, which is an area. Okay? So here we would say like between t equals 0 seconds and t equals 5 seconds, the net gain of, we'll think about it, was, and maybe we would get something like 10. And if it was a velocity graph before, it'd be feet per second times seconds. That's from the unit analysis. And I would cross out the seconds. They cancel out. So I would have 10 feet. And I would think about, so we start out with velocity, and now I got something in feet. And now you might think about writing net gain of position, because you have the feet units. And you would know not to write net gain of velocity, because velocity is not measured with feet. And again, this is very hard. This is the hardest part. But be aware, there are points on the table just for writing correct units and correct x values. Stuff that's very, very easy to get. Be careful. Good luck. Watch the next video if you would like a different example besides the velocity example, which you've sort of gotten used to. See you next time. Bye for now.